So take a moment, kind of look through your homeworks 1 and 2. If you see anything that you want to talk about, I'm happy to spend a few minutes here kind of doing that.
Sure, Floyd.
Yes, sir.
Do you know when our test is going to be?
It'll probably be, well, next week's all goofy, right?
Yeah.
But we have, after today, we have one more lesson to do, but we won't be able to fit that in before like all the goofy stuff happens next week. So it'll be like maybe the first class after that goofy stuff next week.
All right.
So like whatever the next class, I'll figure it out and get it on the calendar, but it's, we have one more lesson after today, and then we'll have a review day, and then we have those synchronous days, so I might I don't know what we'll do with it might just be like more review, like continue to work on your review or whatever. I don't know.
All right.
I haven't figured it out yet.
Thank you.
Yep. Foxy. Yes.
Can I see question 7 on homework 1?
Yes. And I'll get right back with you, Hallie.
Okay.
It's a little bit easier to come back to the in-classers than the Zoomers, But I'm going to get you. You said 7? Is that correct, Paradise?
Yes.
Okay.
Thank you.
You're welcome. All right, so this is a multiplication problem, so I'm just going to start by factoring everything to start with. So multiplies to give me -12 and adds to give me -1 is -4 and +3. Multiplies to give me -20 and adds to give me +1 is +5 and -4. Multiplies to give me 35 and adds to give me 12 is +7 and +5. And then multiplies to give me +21 and adds to give me +10 is +7 and +3. So now I'm just going to go to look to reduce. So the x minus 4s can cancel. The x plus 3s, the x plus 7s, and the x plus 5s. Since everything canceled out, they're all replaced with 1s. And 1 times 1 times 1 times 1 is 1, and 1 over 1 is 1, so this is just 1. Paris, you feel good about that?
Yes, thank you.
No problem. Halle Berry, what you got?
Well, I was wondering if you could do a chapter of second you could possibly do number 5.
I can do them all. If you'd like to see number 5, I'm happy to do that. It is super possible that I do them all, but I don't really, we're not going to do that in class. All right, so I'm going to start by factoring. So the first denominator, I can just take out a greatest common factor of 2. The second denominator is a difference of 2 squares, so that's x minus 5 and x plus 5. So my least common denominator has got to have that 2. It's got to have the x plus 5, and it's got to have the x minus 5. Good so far? If I'm going too fast or you don't understand something I'm doing, anybody stop me, and we can repeat or slow down or whatever, Sometimes I just get excited about stuff. So if I look at the first fraction, I'm missing the x minus 5. So that's what I'm going to multiply the top and bottom of that one. And when I look at the second fraction, I'm missing the 2. So that's what I multiply to the top and bottom of that one. So there I'm here. So far, so good? Okay. Can I reduce things at this step? No. Why not? There's an addition sign outside of the parentheses. Does that feel okay? Remember, we can only reduce when all we have is multiplication going on outside. Hi, come on in. So I'm going to start by multiplying this piece out and multiplying that piece out. And then we'll combine my like terms in the numerator. It's okay with that, Hals? Okay. And then the last thing I should do is I should check to see if I can reduce what I have here. So to reduce, I would need to factor that numerator, but there's not two numbers that multiply to give me 13 and add to give me -4. So I would be done at this point. So it can't factor, so I know I can't reduce it. Cool? Okay. Yup, no problem, my dude. Joe.
I have two questions, but they're about homework one.
Okay.
The first one, just a general question for multiplication when you're doing the crossing out. If it's a negative, like let's say it's x minus x plus a positive 6, do those two cross out or no?
Absolutely not.
No, okay. Well, no.
So the one thing that you might be able to do there, Joe, is if you had like x minus 6 and then 6 minus x, you can like factor out a -1 in that denominator, and then you could cancel them out.
Oh, okay.
But you can't take x minus 6 and x
Right.
plus 6. There's no canceling that can happen in that one.
And then, could you go over number 3 on homework 1, please?
Sure. So I notice both of these have a leading coefficient that's not 1, but if I look carefully, there's actually a greatest common factor in each of these, and I'm going to deal with that first, because maybe the greatest common factor will take care of my leading coefficient problem. So if I look at the first one, I notice that each coefficient is divisible by 2, so I can at least take out a 2, and each variable part contains an x, so I can take out a 2x. In the second one, I notice each coefficient is divisible by 6 and contains an x squared, so I'll take out an x squared, or 6x squared. So far, so good?
Yep.
Now, multiplies to give me -35 and adds to give me -2 is -7 and +5. And then in the denominator, multiplies to give me -7, adds to give me -6 is -7 and +1. So I can reduce the x minus 7s. I can reduce an x from the x squared. And I can reduce a 2 out of the 6. So that's going to leave me with just x plus 5 in the numerator, and then 3x, and then x plus 1 in the denominator.
Looks good.
Cool. Hi. Come on in. Okay. Claire, for you. Okay. Anybody else? Megs. Okay. Do I have that already? I don't think I do. Let's go grab that. All right. do is to flip the fraction on the right and turn it into a multiplication problem. I'm going to do that at the same time I'm doing my factoring, just so I have less stuff to rewrite. Is that okay? So I'm just condensing those two steps together. So the x cubed plus 1 is a difference of 2 cubes. So I'm going to factor that using my difference of 2 cubes factoring pattern. Again, if we don't remember that, that was our difference of 2 cubes factoring pattern. In this case, my a is x and my b is 1. Pretty easy to do that difference of 2 cubes. Okay. If I look down at the denominator, I notice there's a greater factor of 5x squared. And the x squared minus 2x minus 3 factors, because the numbers that multiply to give me negative 3 and add to give me negative 2 are negative 3 and positive 1. So far, so good, Megs? Okay. Now, the x squared plus x plus 1 isn't factorable because there's not two numbers that multiply to give me 1 and add to give me 1. So I'm just going to stick that in the denominator. Remember, I'm flipping here at the same time as I'm factoring. And then the 10x to the fourth plus 10x to the third, well, I can take out a greatest common factor of 10x cubed, leaving me with x plus 1. And now I'm going to look to factor, or I'm sorry, to reduce. So the x squared plus x plus 1 I have in both the numerator and denominator. The x plus 1 I have in both the numerator and the denominator. The 10 and the 5 can reduce. And then these x squareds can cancel 2 of the x's on the x cubed. So if I look what's left in the numerator, I have x minus 1, 2x. So all that's left is just the x minus 3. And that's as good as I can do. Does that feel okay, Max? Okay, cool. All righty. We guys ready to move on, or do you have some more? I can do more if you need to. That's okay. Woody? Okay. Homework 2, number 4. Is that okay, Woody? Okay. Last call from you guys on questions. Megan? 9, you say? Yep, Hal? Yep. All right. 9. Okay, so I'm going to start by factoring my denominators. So that's a difference of 2 squares. So x minus 3, x plus 3. Multiplies to give me negative 3, adds to give me positive, and then multiplies to give me negative 3 and adds to give me. So my least denominator is x minus 3, x plus 3, x minus 1, x plus 1. Which is pretty gross. Benj, you got it, dude. No problem. Is that okay so far, Megs? Okay. So the first fraction is missing the x minus 1 and the x plus 1. The second fraction is missing the x minus 3 and the x plus 1, missing the x minus, or the x plus 3 and the x minus 1. We multiply everything out in the numerator, so that's going to give me 2. That's going to give me negative x cubed plus 2x squared, and then plus 3x, and that's going to give me 2x cubed plus 4x squared minus 6x. Megan and I having a conversation. You guys are welcome in to intercede, okay? I just want to be clear. All right, let's combine some stuff together. I have a negative x cubed and a 2x cubed, so that's going to give me a 1x cubed. I have 2x squared, another 2x squared, and then a 4x squared. I have a 3x and a negative 6x. And then I have that negative 2. And that x cubed plus 8x squared minus 3x minus 2 is only going to be factorable by grouping, but I can take a look at that pretty easily and tell that I can't factor by grouping, right? If you tried to make two groups, the first one you'd have x times, or x squared times x plus 8, and this just have negative 1 times x, or 3x plus 2, and that's not going to cut the mustard. So this is as good as we can do. This was the worst problem on this sheet, I think. Specifically because I kind of screwed up, and my greatest common factor, or the least common denominator, was kind of a bear, right? So you had all these cubes and stuff rattling around in there. It's just kind of a tedious problem. It's because there's so much to keep track of. But again, like staying organized and seeing what you're doing is, real important. And if you have to write down more stuff than I do in order to do that, you surely should do that, right? I try to write down enough stuff so that you're able to follow it, what I'm doing, and especially as I'm talking through what we're doing. But if you find that you're having trouble keeping track of everything with writing as little as I am, then don't do that. Write more. The point is to get the correct answer, and to demonstrate how you're getting the correct answer. And if you have to show more than I do to do that, that's okay. You probably don't want to show less than I am, because you still need to kind of show me how you're getting there. But if you need to write down more, that's certainly okay, and you're encouraged to do that. Some of us have different abilities about, what they're able to hold into their head and what they're able to keep track of. And you guys are just learning to do this, so if you don't feel good about that ability, that's okay. That's fine. Good spot to be at. You're not a bad spot to be at, or not an unreasonable spot to be at. So if you need to write down more than I do, you should do that, okay? And there's nothing wrong with having to write down a lot more and show a lot more work. That's okay. If it helps you keep track of what's going on, that's the point of writing it down, Okay. Let's move on then for today. Yes? C. And just like before, when we talked about reducing or multiplying or dividing or adding or subtracting, I kind of drew an analogy from something that we've already done before involving fractions to kind of use as our scaffolding to kind of extend to this more general setting. We're going to do the same thing here today. So I'm going to start with some simpler problems, some linear equations that you guys have already solved in your previous courses. Talk about like what are some of the ways that we use to solve that. Pick kind of the one that will work the best for us as we extend this to deal with rational stuff. So we'll start with something like this. This type of an equation has a special name. This is called a proportion. That is that we have. Does anybody remember how we solved a proportion? You would have done this quite a bit last year in your geometry class when you dealt with similar triangles. Hals. This is where we cross multiply. Yes, cross multiplication is a solving technique of a proportion. Good. So what we do is we multiply diagonally. So x times 5 is 5x, 2 times 3 is 6, so we have that 5x is equal to 6. This is great because now we have an equation that has no fractions in it, which is probably everybody's preference, right? From here, it's very easy. We can just divide by 5, and there's our answer. Boom, no big deal, right? So far, so good. So this is a technique that you've used before. I know you would have used it last year in your geometry class. Sally says she remembers it from even earlier than that. Let's see what this looks like now when we do this with rational functions. Okay. So far, so good. So just like before, we're just going to do our cross multiplying. And so when we have two parentheses right next to each other like that, what do we have to do to multiply them together? Foil it out. So I'm going to skip showing all the foiling steps and just kind of write down the finished product if you guys are okay with that. Seems like you have been in the past, which is why I'm not reluctant to do that now. But I'm announcing that I'm doing it whenever I do it, just so that you're like, wait a minute, how did you go from that to that? All I did is foil, man. I just didn't show all the steps. Have I told you how I'm doing these in your head so quickly? If you add those together, you're going to get the middle. And you multiply those two together, you get the end. That's it. Provided that the leading coefficients are 1. If the leading coefficients aren't 1, then you're probably better off foiling it because it gets a little bit more complicated than that. But on things that are monic, where the leading coefficient is 1 and the degree is 1, it's really easy to foil them out in your head. Anyways, so what I'm left with is two quadratics that are equal to each other. But that's not a big deal because if I subtract x squared from both sides, it's not really quadratic, is it? So what I'm really left with is a linear equation that should be pretty easy to solve. So I'll add x to both sides to cancel the x's on the right, and I'll subtract 5 from both sides to cancel the constants on the left. So 6x plus x is 7x, and negative 6 minus 5 is negative 11. Is everybody okay with what I did there? I just did all that stuff in one step, right? I just did a bunch of subtracting or adding things to both sides. We're okay with that? Just like you would have done in your algebra course. I just did a lot of it there. And then I'll divide both sides by 7. And there's my answer. Now there's a couple of things that I want to point out here. So first, you notice here that we ended up with a linear equation. That's not always going to be the case. You could end up with a quadratic equation. Some of those quadratics will be factorable, but some of them might not be. What might you need to do if the quadratic is not factorable? You have to use the quadratic formula. So this one, it was quite easy because what we ended up really was linear, so there wasn't much to worry about. But you could end up with something that's quadratic that's a little bit more challenging to solve, but we did spend a whole chapter worrying about solving quadratics here not that long ago, so we should still be fairly comfortable with that skill. The second aside that I have is the answer that we get at the end is not always an answer. So much like when we solved absolute value equations in first semester, it is possible to get extraneous solutions here. But the check to see if our answer is extraneous is much easier than it was when we dealt with absolute value functions. The only thing that we need to do with our answer to check it is make sure it doesn't create a zero denominator. So if I take negative 11 over 7 and I plug it in here, do I get 0? No, right? Negative 11 over 7 plus 2 isn't 0. Everybody's okay with that? I have to check it here, which again, doesn't give me 0. You don't have to write anything down to do that, but you do need to make sure that you are checking that, because on occasion, you're going to get an answer that gives a 0 denominator, in which case you just discard it. And whatever you're left with is your solution, and if you have nothing left, then there is no solution. Is that okay, Megan? All I'm doing is I'm checking my answer to make sure that it's not giving me a 0 denominator. So if I plug negative 11 over 7 into either denominator, it doesn't give me 0, right? Because negative 11 over 7 plus 2 isn't 0. It's, 3/7 or something. And negative 11 over 7 plus 5 isn't 0. It's, 3 and 3/7 or something. Is that, Joe?
So if it does equal 0, that's when we have...
You would you'd cross out whatever the answer is that creates a 0 denominator.
Okay.
If you have anything else left, because you can get more than one answer because you might have solved the quadratic and gotten 2 answers,
Right.
then the other, whatever's left, is your answer.
Okay.
And if nothing is left, then there is no solution.
Okay.
So just like we did before with the absolute values. Again, this is easier check because you really don't need to do any algebra here. Basically you can do this by inspection and just kind of looking at the problem. Right? The only thing that is going to make x plus 2 0 is negative 2. Well, that ain't negative 2.
Right.
And the only thing that's going to make x plus 5 0 is negative 5, and that number ain't negative 5, so...
And you always check with the denominator.
Only the denominators. We do not care about the numerators.
Okay.
Yes. So again, our extraneous check is just to see if the answer makes the denominator equal 0. And again, it doesn't happen very often, but it does happen on occasion. You just need to be aware that that could happen. Okie doke. So the other solving situation, or the other type of solving situation that we could run into would be something like this. So this is, again, something that you probably would have done in your algebra or pre-algebra class, that kind of a solving problem. Notice that this is not a proportion, because on the left-hand side of the equation you have two fractions, not one. Everybody notice that? So this is not a proportion. This is a recall, not an example. But let's talk about a couple of different ways you could have gone about doing this. So one thing you could do is you could add the fractions on the left-hand side to make a proportion. And then solve as if it's a proportion.
Can you always do that? Are these strategies like kind of pick one, or is it based on this?
I'll summarize here in a minute and talk about what to do. The other option is you can make a least common denominator with everything. So you have the same least common denominator on both sides. And then you can just set the numerators equal to 0, or equal to each other. Let's just say the left-hand side numerator equal to the right-hand side numerator, and solve. And the third technique is called clearing fractions. That is that we multiply both sides by the LCD and then solve. Now, of these three strategies, all of them are valid, really, in any case. But the one that I think is the best overall strategy is this idea of clearing fractions. And I'm going to say for a couple of reasons why that's the case. So the number one reason is, if we talk about our operations on fractions or operations with rational expressions, which one was harder, multiplying and dividing or adding and subtracting? Adding and subtracting is definitely more tedious, right? You have to factor everything, and you have to make a common denominator, and you have to multiply the numerators out and combine them all back together, and then check to see if it reduces again, versus multiplying and dividing, where all you have to do is factor and then cross stuff out and you're done. Right? The advantage of clearing fractions is there's no adding and subtracting of fractions ever going to be involved, which is nice, right? The other advantage is that it scales really nicely. Like, if you're doing this correctly, the problems always get simpler, and you really never have a fraction past that very first step, which again is awfully nice. So that's the one that I'm going to use, and that's how I'm going to do all the solvings. Now, these other two methods are still fine. They work. There's nothing wrong with them. If you use that method, that's fine. It's not a big deal to me. I'm not going to do that, I'm going to just stick to one method that I think is the most versatile and scales the best. And I think is the most efficient. But if you decided to do something else, I wouldn't mark it wrong as long as you're doing like a correct strategy. Is that okay, guys? I just don't want to do all three of them because it gets confusing, right? They all kind of blend together and then it makes a mess. So I'm going to pick the one that I think is the best one. In my experience, is the easiest one to use and execute. And then we'll kind of go from there. Okay. So what we will want to do first is figure out what the least common denominator would be, looking at all the denominators in the entire problem. So in this case, it's easy to see that that would just be 2 times 3 times 5, since all of those are primes, right? So what I'm going to do is I'm going to multiply both sides by 2 times 3 times 5. And I'm going to write it as a fraction over 1 just so I don't get confused. So those kind of distribute. So I've just rewritten the problem after distributing that least common denominator through. So everybody's okay so far? So now I'm going to reduce. And you'll notice what's happening in each case is I've completely reduced the denominator in each of these multiplication problems, right? So in the first problem, or first piece, I'm left with 3 times 5 times 1 times x, or just 15x. And then I have 2 times 5 times 2, or 20. And then I have 2 times 3 times 7, which is 42. And I'm left with something that's super easy to deal with now, right? So here I can just subtract 20 from both sides and then divide by 15. And I'm done a-rooskies. Notice at no point in here did I actually have to add any fractions together, right? I didn't actually make a common denominator. My fractions were gone after the first step. After I did the multiplication and reduced, everything was just a linear equation. It was much easier to deal with.
It's so nice.
Yeah. I think it's a really useful technique, and it scales really well to rational functions. So let's look at an example now dealing with rationals. Again, I would prefer, if your early algebra or pre-algebra teachers taught that as a standard technique. I don't know that that's always been the case with fractions, as we like to make common denominators all over the place and combine everything, and I think makes the problem harder than it needs to be. But I think that's a really useful technique. All right, let's see here. All right, so I'm going to start by factoring the denominators. Really, I would factor everything, but clearly the numerators don't factor at all. Oh my goodness. Hold on one second here, folks. I need to not be a moron. And actually, let's do it this way. That'll be an easier fix. Let's just do that. I'll make that 16 instead of 4. That's an easier fix. So I've done my factoring. I'm going to identify my least common denominator, which is x minus 4 times x plus 4 times x plus 1. And then I'm going to multiply both sides of my equation by that least common denominator. And notice here I just wrote it as LCD instead of having to write all that stuff down since I've already listed what the LCD is earlier. Just in the interest of not having to try to squeeze that all in there. But I am going to write it all out on that because it, I think, makes things a little bit easier. Okay, so now I'm going to reduce. In the first fraction, the x minus 4 and the x plus 4 reduce. That leaves me with x plus 1 times x plus 1. In the second fraction, the x minus 4 and the x plus 1 reduce. That leaves me with x plus 4 times x minus 2. And in the last fraction, the x plus 4 and the x plus 1 reduce. That leaves me with x minus 4 times x plus 3. Yes, sir.
Can I use the restroom, please?
Absolutely. No problem. Which, again, pretty good deal because all the fractions are gone, right? Now, there's a lot of writing to get there. I admit that. But there's going to be a lot of writing to get to any of the solving places, regardless of what you're doing. The advantage here, though, is that all the fractions are now gone, right? We're just dealing with a polynomial, which is something we should feel okay about. So I'm going to multiply each of these out. So I'll FOIL out